Okay, so let's cover chapter 5 of Tao's analysis. In this video, we're only going to have time for Cauchy sequences, and next video we'll go over some of the properties of the ordered statements. Okay, let's start with Cauchy. So we're going to start off chapter 5 with the Cauchy sequence of rationals. Remember, last chapter we defined rationals. So the Cauchy sequence of rationals is a sequence. Okay, that's standard notation of sequence. Of rationals and just assigns a value to each n, and that's an. Okay, standard. Um, so that's a sequence. Now, what makes it a Cauchy sequence is we can denote the concept of epsilon steadiness. So epsilon steadiness means that for every epsilon, or not for every epsilon, that's if epsilon greater than 0, then an n equals 0 to infinity is epsilon steady if and only if for jk greater than 0, then any aj minus ak, the distance between the two is less than or equal to epsilon. And now we see that a Cauchy sequence is an n equals 0 to infinity. So we can say that this is eventually E steady, right? E steady. So eventually epsilon steady. So we say that a Cauchy sequence is a sequence that's eventually epsilon steady for every epsilon greater than 0. Okay, so to see some examples of a Cauchy sequence, we can consider, let's say, an is equal to 1 over n, right? So this is going to be the sequence an. Obviously, we can't do 0, so we'll start at 1 and we'll go to infinity. Now, for every epsilon greater than 0, we want to find some, let's just say we want to find some n greater, there exists some n greater than 0, such that for every j and k that's greater than this n, then what we have aj minus ak is less than or equal to epsilon. And I guess this shouldn't be 0. I'll start this at 1, because that's what the n starts at. So how do we prove this? Well, we substitute what is. So we know that aj is less than or equal to 1 on n, right? And we know that ak is also less than or equal to 1 on n. So therefore, like, the absolute value of the difference is less than or equal to 1 on n. Now that we have this, we just have to choose epsilon greater than or equal to 1 on n, right? Because, so for every epsilon, we can, well, for every epsilon, we want to choose an n. So we choose the epsilon that's greater than or equal to 1 on n. So we choose the 1 on n that's less than or equal to epsilon. And we can do this by the property that states that for every rational number, you have this Archimedean property that n times epsilon is always greater than k for any positive k. Number k. We proved this in section 4. Using the Archimedean, using the Euclidean property, actually. Okay. Let's move on to bounded sequences. So bounded sequences states that it's just a bound for the sequence. So if M is a bound for an, then all an's are less than or equal to M. Okay. So one thing that you can show is that every finite sequence is bounded. How do we? It's a very easy proof. You just take, you just induct, right? So you say, okay, well, obviously 1 is bounded by just that one element, but assume that like a1 through ak is bounded. We want to prove that ak plus 1 is bounded. Well, what do? We take the bound of this, which is m, and we take max of m and mk plus ak plus 1, and it's obviously bounded by this. Another thing that we can prove is that every Cauchy sequence is bounded. Why? Well, what we can do is let's just so what's a Cauchy sequence? For every epsilon greater than 0, there exists some n's such that if j and k are greater than n, then we have aj minus ak is less than epsilon. So let's choose epsilon to be 1, right? So we're gonna, if this is true for every epsilon greater than 0, it's definitely true for epsilon equals 1. So for every epsilon such that j, k greater than or equal to n, you could do any epsilon. You don't have to do 1, but 1 is like an easy number to work with. So what you can do here is that you split into two sequences, right? So if you have an n equals 0 to infinity, split into the finite portion, which is, well, I guess it would be an minus 1 n equals 0 to infinity. And this is bounded, or sorry, this would be an n equals 0 to n minus 1. This is bounded by m, let's say. We also have an n equals n to infinity. And we want to prove that this part is bounded. And if once we have that this part is bounded, we take the max of both and it bounds the whole sequence. So what we can do is we note that, let's just take an, right? So a big N. So a big N minus any aj in this sequence is less than or equal to 1. So what does this mean? Well, what this means is that using the triangle inequality, that if an minus aj is also less than or equal to like the sum of these. So what we have here is that we have that for any aj, uh, okay, so because we have an minus aj is less than or equal to 1, what we can do is we can prove that the absolute value of any aj is less than or equal to the absolute value of an plus 1. And for boundedness, we're going about absolute values, right? We're not just going about regular things. So how do we prove this? How do we get from here to here? Well, consider if I just subtract like this, and then I use triangle inequality and say that that's true. All right. So therefore, because every aj is less than an plus 1, we just take max of m and an plus 1. Okay, now let's move on to 5.2. So 5.2 is all about equivalent Cauchy sequences. So it's basically saying that when are two Cauchy sequences the same? So again, we do epsilon closeness for sequences. So if we have two sequences for an, like this, and bn, like this, we say that they're epsilon close if that for every n, an minus bn is less than or equal to epsilon. We say it's eventually epsilon close if there exists some m such that for any n greater than or equal to m, then it's eventually less than or equal to epsilon. And of course, they're equivalent if, so an n equals 0 to infinity, and bn equal to 0 to infinity are equivalent, if for every rational, so for every epsilon greater than 0, epsilon is rational, an n equals 0 to infinity, and bn n equals 0 to infinity are eventually epsilon close. Okay, so now we can prove that, I'm not going to go further proof here, but it's fairly simple. We can prove that equivalent sequences are Cauchy if one of them is. So if one sequence is Cauchy, the other is. And also boundedness works. If one is bound, then the other works. Okay, let's move on to 5.3. In 5.3, we construct the reals. So what do we denote? We say that for every Cauchy sequence, this is just like the trick we do. We denote LIM, so big LIM. So big LIM for n goes to infinity of an is just a number that we assign to rational Cauchy sequences. And the LIMs are equal if the Cauchy sequences are equivalent. So what does it mean? This isn't a limit, this is LIM. Later we'll see like, oh, wait a minute, it actually has to do with the limit and convergence and stuff. But that's later, that's next chapter. Now, we can prove that this is a valid equivalence relation, right? You have reflexivity, symmetricity, and transitive property. Now, what you can say is that I'll define the addition of two Cauchy sequences by saying LIM of n goes to infinity of an plus LIM of n goes to infinity of bn is defined as LIM n goes to infinity of an plus bn. That's the definition. Now, what you can show is that if an is a Cauchy sequence and bn is a Cauchy sequence, then an plus bn is a Cauchy sequence. So, okay, it's nice and well defined because you can show that it's well defined, right? And you can do all that cool stuff. Now you do the same thing for multiplication. If LIM, n goes to infinity of an times LIM of n goes to infinity of bn is defined as LIM n goes to infinity of a and bn. Now, same thing here. We can prove that if we have one Cauchy sequence and another Cauchy sequence, then the product of two Cauchy sequences is Cauchy. So I'll just go over this proof because I like it. But what it says is that, so choose some j and k from an, so aj and ak. So, and same thing for b. Then you take aj bj minus ak bk, and that's what we have here. Now, what do we have to prove? We have to prove that if this is Cauchy, then, well, this is less than or equal to any epsilon that we throw at it. Well, what is this less than or equal to? Then we note that this is equal to aj bj. This is a trick that is kind of helpful sometimes. You add and subtract the same things. Now use triangle inequality. So on the one hand, we have aj. We don't know what aj is, but we know that this is bounded, right? So let's say this is bounded by m1, this is bounded by m2. So we know that aj is bounded by m1, so we don't know what aj is, so we'll just put m1. And we factor, of course, so we get bj minus bk. Same thing here, we get plus m2, aj minus ak. Now, how will this be eventually smaller than any epsilon? What we can show is that there exists some epsilon such that for any epsilon, we know that this is bounded, and for any epsilon, we know that this is bounded. So we'll choose epsilon 1, epsilon a, to be equal to epsilon b, equal to epsilon over b1, m1 plus m2. Why? Well, now I carry this over. m1 on epsilon plus m1 plus m2 plus m2 times epsilon on m1 plus m2. And what do we have? This is less than or equal to epsilon times m1 plus m2 on m1 plus m2, which is less than or equal to epsilon. And we're done. Now, That's addition and multiplication. What about subtraction? Well, we just define negative lim as lim of the negatives. As lim of the negatives. Okay, pretty straightforward there. Then we can obviously define subtraction as adding the negative number. Okay, now division is the hard part. So in order to do division, we have to define the notion of zero, right? So you can't divide by zero. So how are we gonna make it so that we can't define by zero in our notes? So we say that a sequence is bounded away from zero if there's a rational C such that it's every n is um, for every n greater than or equal to 1, then we have the a n greater than or equal to c. So this is bounded away from 0 if there exists a rational c greater than 0 such that all the a n's are greater than or equal to that c, right? So it can't have 0. Now, we say that um, if x is a non-zero real number, then x is equal to the limit n greater than or equal to infinity, not the limit, at lim of a Cauchy sequence that is bounded away from 0. So basically, we know that real numbers are Cauchy sequences, but now we're saying we can take out the 0. Okay, so we can write, let's say x is the limit of some an. Okay, so now one thing that we can do is we can prove that every Cauchy sequence has an equivalent Cauchy sequence. So every Cauchy sequence has an equivalent Cauchy sequence Bn such that Bn is bounded away from 0. How do we do this? Well, if Bn is bounded away from 0, and so what's it called? If this is equal to x and x not equal to 0. So if Bn is bounded away from 0, what does that mean? Then it's not eventually epsilon close to 0. So let's fix our epsilon. So if Bn is not eventually epsilon close from 0, we have a minus 0, but I'll omit it. So if Bn is not eventually epsilon close from 0, what does this mean? Epsilon. Well, Bn is greater than epsilon for some epsilon. What also does this mean? We know that there exists some m such that Bn minus Bm is less than epsilon, sure. We can also do less than epsilon over 2. Okay, now what do we have? We know that every Bn is, there exists some e such that this is true. We want to prove it for any epsilon less than 0. So we have this Bn. Bn is greater than or equal to Bm minus, I'll write it here, greater than or equal to Bm, well, this is equal to Bm minus Bn minus plus Bm. Okay, here's how I'll write it. Sorry, this is getting confusing. I'll write it like this. Bm minus Bn minus Bm. Okay? Does that make sense? So you have Bn, then you have a Bm, but you also have you have, what's it called? This thing here. So what you do is you do the less than or equal to thing. This is less than or equal to, so this is less than epsilon over 2, right? So if you have Bn is less greater than epsilon, and this less than epsilon too, but by the triangle inequality, that gives us Bn is less than or Bn is greater than or equal to epsilon over 2. Bm is greater than or equal to epsilon over 2, sorry. This m was arbitrary, so therefore everything is bounded by epsilon. Okay, so now what we can do is we say that if an is Cauchy and bounded away from 0, then we take this, and this is also Cauchy. Yeah, it's not too hard to prove this. You just do that. Like you take this, like the one on AJ is minus one on AK is equal to absolute value of AJ minus AK on AJK. And this is bounded, right? Away from 0. So we'll let this be bounded away from 0 by C. So therefore, if this is bounded away from 0 by C, then all of these are greater than or equal to C. So we can C becomes C squared. And here we have AK, AJ minus AK, right? And what we can do is that we can write what we can do is that we can say that an, since this is eventually less than epsilon, it's also bounded by c squared epsilon, so we get the c squares to cancel out. Okay, so now we'll just define the reciprocal to be the lim of n goes to infinity of an reciprocal. Now we can prove that reciprocation is well defined and all that good stuff. And now we have division, right? We'll define a divided by b to be lim of n goes to infinity of the an's times the lim of n goes to infinity of the bn reciprocals. Okay, so now, sorry if that was a bit confusing. Let me know if you have any questions. Yeah, that's going to be it for today's video.